Hi everybody, this is Dr. Bricker here with the video for the remainder of Chapter 8. Remember, we're covering Chapter 8, the first section through the third section. We're not doing stretching or compressing of materials. Okay, so in class, we ended up on this slide, and we went through this problem, and we also looked at problem 8.1, and I want to continue through a few more slides to get us through section 8.3, and perhaps work on some of the homework questions along the way. Okay, so in this chapter, it's about equilibrium, which means balancing forces. So forces are from chapter 4 and 5, but also balancing torques. So some problems you need to consider both forces and torques to look at equilibrium. Okay, so let's look at the next slide. Okay, so this problem is called Will the Ladder Slip? So we've got a 3-meter long ladder. It leans against a wall at an angle of 60 degrees, so you can see that in the picture. What is the minimum value of mu sub s, the coefficient of static friction with between the ladder and the ground, that will prevent the ladder from slipping? Assume that the friction between the ladder and the wall is negligible. Okay, so you see the picture. There's the ladder, center of gravity. We're assuming it's right in the center of the ladder here. The overall length of the ladder is 3 meters, and we're assuming there's no friction up here between the ladder and the wall, but there is friction here that keeps it from sliding out. And we want to calculate what's the minimum value of mu sub s. So what is the coefficient of static friction? Now the mass of the ladder is not given. Usually that triggers a little bit of anxiety, but if anything again is ever going to cancel out, it's going to be the mass. So let's set this problem up and see what we can do with it. Okay, so let me kind of draw the picture out here. So you've learned from these problems that a picture is really important. Here's the ladder on the wall. The length of the ladder is 3 meters. 3 meters. Theta is, in the problem, 60 degrees. And we want to know how much is mu sub s, the coefficient of static friction. And in the previous picture, you saw that this distance was d2. We'll see why that's necessary in just a moment. This is theta, so we're assuming it's a uniform shaped ladder. So here's the weight, and here's the line of action of the force of the ladder, of the weight from the ladder rather. Up here we have N2. That's the normal force from the wall on the ladder. And down here we have N1. That's the normal force from the ground on the ladder. And then we have static friction here. Okay, and then there's no frictional force between the ladder and the wall. Now if we were going to try to do this problem with just looking at forces, we could try that. Let's try to do that actually. So in terms of doing that, we know that at normal 1 is equal to the weight. Okay, so those are the only up and down forces. We can't solve for the normal because we don't know how much the mass is. We can't really use that so easily. And also this is equal to m times g. Okay, again, I'm just writing down what I know. I'm trying to figure out how to solve this problem. We know that static friction is equal to N2. Okay, that's balancing the forces left and right. Static friction being left, normal 2 being right. Same thing, I can't solve that because I don't know what normal 2 is. So lots of things that I don't know. This is good. This is a good place to start. So this is just using forces. Maybe we could use torques. If we use torques, maybe we could figure out what the force of static friction is. Okay, so let's look at that. Just one other thing to add before you start looking at torques. The definition of static friction. So remember, static friction is less than or equal to the normal force, in this case normal 1 times mu sub s. Okay, and I know that normal 1 has got to be equal to the weight. So if I wanted to, I could say static friction less than or equal to normal 1, or I know it's equal to, I know normal 1 is equal to the weight. So I could also say the weight, or the weight times mu sub s, or mg times mu sub s. Okay, that's just looking at the definition of static friction. still I can't solve for mu sub s yet. I would be able to know what it needs to be from this formula. Looking at this, static friction divided by the weight is less than or equal to mu sub s. So if I can somehow get static friction or weight, I can maybe use that. Okay, so this is one of those problems. I always say this is the hardest problem of the semester. So far, this is going to be the hardest problem of the semester. But that's okay. We'll work through it and see if we can solve it. Okay, let me erase this. Okay, so let's use torques. Let's pick this point down here as the pivot point. So I'm going to circle that. That's going to be the pivot point. And I'm going to look at the torques about that pivot point. And the ladder's not going anywhere right now, so the torques are going to be balanced. Okay, so about this pivot point, I'm picking this as the pivot point because then I don't need to know normal 1 or the force of static friction because they are acting at that point. So there's no torque because of N1 or static friction at that point. Okay, so let's balance the torques about that point. I've got the weight force making it rotate counterclockwise at a distance of d1 from the axis of rotation. So you have a better picture, but this was d1. So relative to that pivot point then, I've got the torque from the weight equal to the torque from N2. So if that's my pivot point, the weight force would make it rotate counterclockwise. Normal 2, that's the other force that's not at the pivot point, it's over there at D2, will make it rotate clockwise. So the torque from the weight is equal to the torque from normal 2. So the torque from the weight would be the weight force, and then the perpendicular distance to the pivot point, which in the problem is D1. That's got to be equal to the torque from normal 2. So the force is normal 2, and then the perpendicular distance to the pivot point is D2. Okay? Okay, so far the physics is great. We've looked at the forces, we've looked at the torques. How are we going to put this all together? Well, so don't forget we have this relationship. And this, again, is going to be a problem that has several different layers. I know that static friction has to be equal to normal 2, so let me actually solve for normal 2 in the formula that I just have over here. D1 over D2 is equal to N2. This is again just from the torques. But I also know that N2 has got to be equal to the force of static friction. Okay? And then I also know that the force of static friction down here, change colors here, this force of static friction down here divided by the weight is less than or equal to mu sub s. So I've got a lot of pieces of information floating around. I'm about to put them all together. Okay, so again, normal 2 is equal to the static frictional force, as you can see here. So let me plug that into the formula down here. Okay, so just to recap, normal 2 is equal to static friction, and I'm going to take that and plug it in here. Okay, so when I do that, normal 2 is the weight, d1 over d2. I'm plugging that in again here for static friction, and then divided by the weight turns out to be less than or equal to mu sub s. So I don't need to know the weight. The weights cancel out. So d1 over d2, mu sub s has to be bigger than d1 over d2. So the minimum is when it's equal to it, and then anything greater than that, we're good to go. Okay, so you just have to figure out what d1 and d2 are. And you can do that because you know this length here. You know this length. So you can figure out d2 because you know the angle there. So the sine of theta is d2 over L. So you can get d2 because you know theta and you know L. So you can figure out d2. And then the distance from the weight force from the pivot point is L over 2. So then you could also find out d1, right? This distance is L over 2 down to here. So then you can find out d1 from that. Okay, very good. So lots of different things going on. We actually needed to use balancing forces and balancing torques. And then it all came together here at the end that mu sub s is bigger than d1 over d2. And you still have to do a little bit of work to get d1 over d2. Okay? Very good. All right, let's look at some problems from the homework. Okay, here's a problem from homework 9. So chapter 8 questions are from homework 9, which is actually due December 2nd at 4:59 p.m. So in this one, you're carrying a 3-meter long, 23-kilogram pole to a construction site when you decide to stop for a rest. You place one end of the pole on a fence post and the other end 35 centimeters from the tip. On the post, and you hold the other end of the pole 35 centimeters from the tip. Okay, so one end's on a fence post, you are on the other side, but not at the end, 35 centimeters from the end. For the steps, you can take a look at the video tutor solution here, so that's available to you. How much force must you exert to keep the pole motionless in a horizontal position? Okay, so the fence post is kind of helping you out, but you're taking some of the load. How much do you take? So you're not splitting it in half because you're not holding it in the same spot as the fence. So we need to have a nice picture for this one. Let's take a look at it. Okay, so here's what you see in the picture. Here's the pole that you're carrying here, and it's 3 meters long. This end is resting on a fence post. This end is resting on your shoulder, so I just called it, there's a picture here, shoulder. I represented it just by some kind of like something that's sticking on. It's a uniform pole, so the weight force from the earth is straight down here, so this is mg, and it's right in the middle. It's a 3-meter long pole, so this is right in the center, 1.5 meters from either end. It's resting on the fence here, so there's a normal force from the fence. Now if we wanted to look at forces, we could say all the force is up. So I'm holding it up with my shoulder. The fence is holding it up, and that's equal to the weight. So really in this problem, again, what they're asking for is, how much is the normal force from your shoulder? Now again, it's not half of the weight because you're not holding it on the opposite end like the fence is. You're holding it closer to the center of gravity. So we can't just solve this with forces. I can't solve for normal shoulder because I don't know normal fence. But hopefully with torques I can. Again, you're free to pick whatever point you want as the pivot point. So I'm going to pick this as the pivot point where the pole is contacting the fence. The reason I'm doing that is the normal force from the fence does not have any torque at that point if that's the pivot point. So the only torques I have are because of the shoulder force, the normal from the shoulder, and the weight. So let me actually balance torques then. Switch colors back to this. So the torque from the shoulder about that pivot point is equal to the torque from the weight. Now the torque from the shoulder is the force, normal shoulder, distance to pivot point, and you can see here I have 2.65 meters. So from one end to where my shoulder is resting, they say in the problem it's 35 centimeters from one end, so 0.35 meters from the left end. So the distance from the fence to my shoulder then is 2.65. So 2.65 meters, and that's equal to the weight, that's the force, and then the distance to the weight. This is 1.5 meters because it's right in the center, times 1.5 meters. So normal shoulder then is the weight times 1.5 divided by 2.65. And the weight is m times g. Luckily they give us the mass in this one. So 1.5 divided by 2.65. Okay, so you have everything to solve this then actually. So the mass is 25 kilograms, and then times 1.5 divided by 2.65. So normal shoulder, oops, I forgot the 9.8. 1 second here, 25, that's the mass, times 9.8 That's G times 1.5 divided by 2.65. Okay, now I think we have it. 138.7. 138.7 newtons. That's what they're asking for in the problem. For fun, I want to figure out how much the weight is. So M times G, this would be 25 times 9.8, 245. Let me go back up here where I just was looking at forces. So the normal from the fence, is the weight minus normal from the shoulder. So if you put those numbers in, the weight is 245 minus 138.7. That's the normal shoulder. That's what they're actually asking for in the problem. This turns out to be 106.3. So the fence is helping you out. The fence is holding up 106.3 newtons. My shoulder is 138.7 newtons for a combined 245. So if I wanted to make it easier on myself, I would be at the end of the pole, not 35 centimeters from the edge. Okay, let's look at the next one. Okay, so here's the next one on homework 9. This is actually the third problem, and it's from chapter 8. A vendor hangs an 8.4 kilogram sign in front of his shop with a cable held away from the building by a lightweight pole. So the lightweight pole, we're assuming that it doesn't have any mass. That's why they tell us it's lightweight. The pole is free to pivot about the end where it touches the wall. So over here, it's free to pivot. Maybe that's some sort of hinge. I've got the sign over here. What is the tension in the cable? Okay, let's take a look at this problem. Again, for all these, you need to have a really nice picture. So let's set this thing up. Okay, so here's the picture again. You have the hinge at the wall. There's tension in the cable. It's a massless rod that we have here that's holding it up, and there's a sign over here. Usually the sign says physics is fun. This one said something else, but that's okay. And we want to know, again, how much is the tension in the cable. So we can try to look at the forces on this thing. I mean, here's where the tension's at. It's in the cable. It's going that way. So it has a part in the y direction and a part in the x direction, kind of like this. So if that's theta, this is back to being theta. There's really like another tension that's holding the sign up. I'll just call it sign. But really that's equal to the weight, so I'm just going to call it weight pulling down here. Really it's like tension holding up the weight, but they're equal to each other, so I'm just going to call it weight again. Okay, and there's got to be some kind of force this way, like normal from wall or something like that. Normal from hinge. I'll just call it normal from hinge, going that way. The reason I know there has to be this force to the right is I've got this force to the left. Those have to be equal to each other. And in this problem, the whatever forces are up, this one, tension Y, has to be equal to whatever forces are down, which is the weight. Now you might say, well, isn't there like maybe there's an upward force here because of the hinge? And it's possible that there could be. I just, from experience, know that there's not going to be in this problem, just because both of these forces over here, the tension Y and the weight, are making it rotate about the pivot point that would be here. So that means there is no force down there. Okay, we'll work through it, and then it'll become more apparent in just a minute why there is actually no vertical force here at the hinge. I mean, there could be, but there's not in this problem. If this rod actually had some kind of mass, then there would have to be this upward force. But if it's a really massless rod, you could have this situation. Okay, so again, we'll use this as our pivot point. That way we don't need to know the normal from the hinge. We don't need to know anything about any hinge forces. So all the torques are balanced about this point right here. So I've got the torque, because of Ty, has to be equal to the torque because of the weight. Now this one might be a little bit scary because you don't know the actual length here, right? You don't know the length of the rod. So let's just set it up and see what happens. So torque because of Ty would be the force, Ty, and the distance from the pivot point over to the force, and I'm just going to call it L. That's got to be equal to the torque because of the weight, which is the force, the weight, and then the distance from the pivot point to the weight. Again, that's L, right? They're the same distance from the pivot point. The L's cancel out. So in this problem, Ty is equal to the weight, and that's M times G. So Ty turns out to be 8.4 kilograms times 9.8 meters per second squared. So let me actually punch that in. That's just Ty. That's not the overall tension. The problem's actually asking for the tension. So 8.4 times 9.8, 82.32 newtons. That's Ty. So you have to go back to the picture to figure out what the actual T is. You have to use a little bit of trig for that. Let me do this in a different color. I'll use green. So looking at this triangle here, I could say that the sine of theta, or I guess it would be the cosine of theta actually. Cosine theta is, so cosine theta, looking at the green triangle, the adjacent side, Ty over T. So then T is equal to Ty divided by cosine of theta. Whoops, a little carried away with the theta symbol here. Cosine of theta. Okay, so T is Ty divided by the cosine theta. So you'll have to take 82.32 divided by the cosine of 60. Okay? Now the cosine of 60 is the same thing as the sine of 30, which I know is a half. So T is going to turn out to be about 164.64 or so. Okay, so take a look back at that triangle. Convince yourself that the cosine of theta is Ty over T. All right, let's look at one more problem from chapter 8. Okay, so this is a pretty fun one. We did the problem in class, or in the lab, I should say, about looking at the bicep force and looking at torque provided by the bicep muscle and the mechanical disadvantage of the bicep muscle. So this is a similar problem, physiology, but this is looking at the shoulder. So if you hold your arm outstretched with your palm upward, the force to keep your arm from falling comes from your deltoid muscle, as you can see in the picture here. So when you put your arm out like this, it's a deltoid muscle that keeps your arm from falling down. But the problem is a deltoid muscle is really close to the pivot point, 17 centimeters away. The center of mass of your arm is 38 centimeters away. So you have a really small lever arm here, no pun intended, and the lever arm for the center of gravity of your arm is over twice as far away. So you're going to have a really big force just to hold up your arm. Okay, so assume that the arm has a mass of 4 kilograms and the distances are shown and the angle is shown. This is 15 degrees here. What force must the deltoid muscle provide to keep the arm in this position? And by what factor does this force exceed the weight of the arm? So really this is going to give you the mechanical disadvantage of the deltoid muscle. Okay, again, it's kind of like a broken record maybe, but we need to have a nice picture for this to be able to solve this problem. Let's take a look at it. Okay, so here's the kind of the picture that I drew. There's the pivot point right here. And it's 17 centimeters over to where the deltoid muscle is acting. And it's acting at some angle. As you can see that from the picture, here's the deltoid muscle, 17 centimeters from the pivot point. And then the center of mass of the arm is 38 centimeters from the pivot point. Okay? So we want to figure out how much the deltoid force is, using torques. The other thing is theta is 15 degrees. Okay, so let's balance the torques about that pivot point. Get rid of some of this old stuff. Okay, so the deltoid muscle would make the arm rotate counterclockwise, and the torque from the weight would make it rotate clockwise, but the arm's not going anywhere, so those forces are balanced. We can balance torques that way. Okay, so let's actually do that. The torque because of the deltoid is equal to the torque because of the weight. Now remember, maybe going back to the picture, the deltoid force is at some kind of angle. I want the part of the deltoid force, so force deltoid, that's perpendicular to the arm. Okay, so we'll have to do a little bit of trig. I mean, I drew it over here to the right. I could very well, I'm just going to leave it there. That's theta. This would be like force deltoid perpendicular. If that's theta, this is back to being theta. So the sine of theta, from my picture, it's the opposite side. That's this one. So sine of theta, and this is the theta I'm looking at, opposite force deltoid perpendicular divided by the hypotenuse force deltoid. Okay? Now, why do I need to do this? Because when I'm looking at the torque from the deltoid, I need the part of the force that's perpendicular. So I was kind of looking ahead a little bit, actually. But that's okay. So this would be force deltoid perpendicular. That's the perpendicular part of the force times the distance to the deltoid muscle, 17 centimeters. I'm leaving it in centimeters, and you'll see why in just a minute. This is going to be equal to the weight, and then the distance from the weight to the pivot point, which is 38 centimeters. See, the units are going to cancel out. The centimeters part's going to cancel out. You could convert it to meters with no problem. The meters are going to cancel out anyway. Okay, so force deltoid perpendicular is actually equal to force deltoid sine of theta. That's why I did that little part with the triangle there, because force deltoid perpendicular is force deltoid times the sine of theta. And then I have 17 centimeters. This would be mg times 38 centimeters. And then the only thing that you don't know is force deltoid. So let me do one more step of algebra here. Force from the deltoid would be mg times 38 divided by sine theta. And then also, don't forget I've got the 17 here. Okay, so I just solved for force deltoid. That's what they're asking for in the problem. Now, if you wanted to, at this point, you could get force deltoid perpendicular and then go back and figure out what the force deltoid is. That's what they're asking for, force deltoid. I just thought I would do it all in one step here. Okay, and then again, theta is 15 degrees. So let's actually see what we get for this. So the mass, I think they said, was 4 kilograms. Yeah. So we've got 4 times 9.8 times 38 divided by the whole quantity sine of 15 times 17. And I get 339 or so. 339 newtons. Okay? Alright, that sounds reasonable. Let's see what the weight of the arm actually is. So when you do m times g, what do you get? So you get the mass 4 times 9.8. 39.2. Okay, so the deltoid muscle has quite a large force compared to the actual weight that it's holding up, right? This is 339 newtons, mostly because it's at this really small angle, right? The perpendicular part of it is a lot less than that, but anyway, that's the overall deltoid force, 339 newtons compared to the weight, which is 39.2. So part B asks you to figure out that ratio of deltoid force, the ratio of this divided by this. So it's about a factor of, less than 10, but a pretty good mechanical disadvantage there. So just to hold up your arm, it feels like it's pretty easy if you just stick your arm out to the side, but the force that your deltoid muscle is exerting is 10 times more than the actual weight of your arm, just because of where the muscles are hooked up and the angle. Okay, let's go back to the notes. Okay, so we've done a bunch of problems really balancing forces and torques. So stability and balance. So here's a extended object, and the center of gravity is right here for this object in A. Now if this starts to rotate, this will fall back down. Say for B it stopped here. It would rotate back down. But what if for some reason this keeps going this direction? Right here it's still balanced. Here's where the center of gravity is over the pivot point. Now in D, this thing's actually going to tumble over. Here's the center of gravity. So for this one, the torque here's the center of gravity. Here's the pivot point. We're over to this side of the pivot point. So this car is going to fall down. So if you're in this situation and for whatever reason you're driving along, you're fine here, for some reason you flip up a little bit, you're going to go right back down as long as you didn't keep going. If you get to this point, everybody in the car has to run over to this side, and then it'll flip back over. This one, you've gone too far. You're over the pivot point, and you're going to actually tumble over. So that happens with cars. That happens with people. You have to stay over your base of support, or you're going to fall over. Okay, so as long as an object's center of gravity remains over the base of support, the torque because of gravity, remember gravity is a force, it's acting some distance from the pivot point. As long as you're over the base of support, you're fine. Now if you go away from the point of support, you could fall over. So if the object's center of gravity moves outside the basis of support, it's unstable. You're going to move one way or the next. In part C, it's kind of interesting. If you can balance a car here in this position, you set it up, you balance it right here, it's just going to stay here. But if you hit it a little bit this way, it's going to rotate that way. You hit it a little bit to the right, it's going to rotate this way. Okay, so it's an unstable equilibrium because just a little bit of jostling will make it move one way or the other. Okay, here's another example we can take a look at. A cat walks along a plank that extends out from a table. If the cat walks too far out on the plank will begin to tilt. What determines when this happens? Okay, so let's take a look at this actually. Now, if you looked at the center of gravity of the combination of the cat, so here's the cat, here's the center of gravity, the combined center of gravity is here, but here's the center of gravity of the plank. So black, that's the center of gravity of the cat. The black here is the center of gravity of the plank. The combined center of gravity of the system of the cat and the plank is here, the red part right there. Now as the cat continues to walk to the right, the center of gravity of the system keeps shifting to the right. So here, the center of gravity of the cat and the center of gravity of the plank, if you take those into consideration, both of them, of the system, it's right here, right at the edge. So if the cat continues to walk to the right, the center of gravity of the system continues to shift to the right, and eventually the center of gravity of the system will be over to the right of the support, and the thing will actually topple over. Okay, so as long as the center of gravity of the system is over the support, we're fine. The center of gravity of the system gets too far over to the right, away from the point of support, it'll actually fall. Okay. So here's something that you can take a look at. As a human moves, the body's center of gravity is constantly changing. To maintain stability, and I talked about this in class last week, people unconsciously adjust the position of their arms and legs to keep their center of gravity over the support. So if you drop something on the ground and you reach over to pick it up, if it's too far in front of you, your center of gravity will be too far over and you'll actually fall over. So what you do is you kick one leg backwards. So when you kick a leg backwards, as you reach your arm forwards, you keep the center of gravity over the support. And you do this without thinking. You don't think, I need to adjust my center of gravity. You just know from experience of walking around picking stuff up that you have to do that to remain stable. So when the woman stands on her toes, she leans forward, readjusting her center of gravity to be over the balls of her feet. So if you stand over your toes, you've got to somehow adjust your center of gravity to be able to actually do this. As you can see, here's where her center of gravity is in part A, right over the point of support. Stand on your toes. You've got to readjust your center of gravity so her arms have shifted forward slightly. If not, you wouldn't be able to do that. You can actually try it yourself. So go ahead and try this. Stand facing a wall with your toes touching the base of the wall. Now rise up onto your tiptoes. You'll not be able to do so without falling backwards. So if you're right against the wall with your toes there, you need to put your center of gravity over your toes, and if the wall's in front of you, you can't actually do that. So try it. You'll see that you won't be able to. So with the wall in your way, you can't lean forward enough to maintain your balance, so you'll topple backwards. Now, if you could somehow punch your arms through the wall, maybe you could change your center of gravity that way. But if the wall is right in front of you, usually you can't do that. Okay. Here's another kind of trick you can try. Try to balance a soda can, full or empty, on the narrow beveled edge. It can't be done. So if you want to win some money from somebody, say, look, I could balance this can on the edge. Give them the can. They can try it out. You won't be able to do it if it's empty or if it's full. Now, the reason you can't do it if it's empty or full, it's a pretty uniform shape, so the center of gravity is in the center. If you tried to balance it over the edge, the center of gravity would not be over the point of support because the center of gravity would be right in the center. So pretend the can is empty, completely empty. The center of gravity is in the center. You try to balance it on the edge, it's going to fall over. You've got to have the center of gravity over the point of support here. So you can bet somebody, hey, I bet I can have them try it. They can't do it when it's full. I can do it. Then you have to open it, drink some of the liquid, so you can change the center of gravity to a lower point in the can, and then you can actually balance it on the edge. So as long as the center of gravity is over the pivot point. Okay, so if the can is tilted enough to sit on the bevel, the center of gravity lies far outside this point. But if you put about 2 ounces of water in an empty can, or drink some out so there's only 2 ounces left, the center of gravity will be right over the edge, and then you could actually balance it that way. So can completely full or completely empty, the center of gravity is never going to be over this point of support. But if you have about 2 ounces left in the can, then you can actually balance it because the center of gravity will be over the point of support. Okay. So that's all we're going to talk about with Chapter 8, really. There's additional sections, and I put them in the notes, but we don't have time to cover them. Stretching and compressing materials. Cool stuff, and I put it in the notes, but we're not going to cover it. It won't be on the test or the homework. Okay, so that wraps up Chapter 8, and Wednesday we will go over some Homework 8 questions and continue on Wednesday with simple harmonic motion. Okay, any questions, just email me, and I'll talk to you soon. Bye-bye.